All right, let's just dive right in. We have all been there. You're staring down a brand new bottle of ketchup, you've got a burger ready to go, and you're met with absolutely nothing. It's one of those tiny, universal frustrations, right? Well, today we're gonna crack that mystery wide open and find the brilliant science that's hiding inside.
So, you turn it over. You give it a gentle tap. You wait. And that thick, red sauce just sits there, completely defiant. It's basically a solid one moment, just refusing to budge no matter how much you plead with it.
But then you give it a really good, hard shake. You apply some real force, and bam. All of a sudden, it's a completely different substance. It flows freely, sometimes a little too freely, right all over your fries. So what is the deal? How does shaking a bottle magically transform what seems like a solid into a liquid?
Well, the answer has this fantastic name, thixotropy. And this one scientific principle, it doesn't just explain our ketchup problem. Oh no, it explains a whole world of materials that we interact with literally every single day.
The concept itself is actually surprisingly simple. Thixotropy is all about a fluid that basically changes its mind. When you leave it alone, it's thick, kind of like a gel. But the moment you apply stress, shaking, stirring, squeezing, it becomes thin and runny. And as soon as you stop, it starts to thicken right back up again.
Let's break down that technical-sounding phrase. Shear thinning just means it gets thinner under stress. Simple enough. But the really crucial part here is time-dependent. See, unlike something like water, which always has the same thickness, the same viscosity, a thixotropic fluid needs time to react to that stress and then time to go back to its original state.
So how does this transformation actually happen on a microscopic level? Well, it all comes down to a really simple process, breaking things down and then just building them back up again.
I want you to imagine that tiny particles inside the ketchup are like a jumble of logs that have created a dam in a river. When everything's calm, those logs are all locked together and nothing flows. But what happens if you apply a force, if you push those logs? Well, the dam breaks apart and the water rushes through. That is exactly what's happening inside that bottle.
So this all happens in 3 clear stages. First, when it's at rest, that internal structure is strong. It's all locked together, and that's what makes the ketchup thick. Then, when you apply stress by shaking it, you are literally breaking that structure apart, which allows it to flow. And finally, once it's on your plate and you leave it alone, that structure slowly begins to reform. That's why a puddle of ketchup doesn't just spread out forever and ever.
And this entire amazing process hinges on 2 really crucial rules. First, it's completely reversible. The fluid can go back and forth from thick to thin pretty much endlessly. And second, it is all about time. The longer you shake it, the thinner it gets. The longer you let it sit, the thicker it becomes. It's this time delay that makes thixotropy so unique and so incredibly useful.
Now, as cool as this is for ketchup, this property is absolutely everywhere. Seriously, once you know what to look for, you are going to start seeing thixotropic materials all around you.
Just think about it for a second. Yogurt and mayonnaise, right? They need a good stir to get all creamy. Toothpaste squeezes easily out of the tube, but then sits perfectly still on your brush. Paint becomes easy to spread when you're rolling it, but it doesn't just drip down the wall afterwards. Even things like honey and the special mud they use for drilling oil wells rely on this exact same property.
Now, thixotropy is just one type of what scientists call non-Newtonian behavior. It's a really fancy way of saying it's a fluid that doesn't follow the simple rules like water does. So let's quickly compare it to a couple of its cousins just to see what makes it so special.
Okay, this chart shows thixotropy next to a couple of its, let's call them quirky cousins. First you have rheopecty, which is the complete opposite. It actually gets thicker under stress. Can you imagine stirring something and having it turn into sludge? Wild. Then there's pseudoplasticity. This one also gets thinner, but the change is instant. And that's the key difference. Thixotropy has that recovery time built right in. It's like it remembers what it used to be and it tries to go back.
So why should we care about any of this? Well, what starts as just a little annoyance with a ketchup bottle actually turns out to be a key to some major industrial and consumer innovations.
That's right. The very thing that makes you bang the ketchup bottle on the table isn't a flaw, it is a deliberately engineered feature. Scientists and engineers design this property into products to solve very specific problems.
I mean, look at these brilliant examples. You want your paint to flow easily when your brush is applying stress, but you absolutely need it to thicken up the instant it's on the wall so it doesn't drip everywhere. You need your toothpaste to flow out of the tube but stay put on your toothbrush. And in oil drilling, this isn't just clever, it's critical for safety. That special mud has to flow while it's being pumped, but it must become a solid like gel to prevent a catastrophic collapse when the pumps stop. It's an ingenious multi-million-dollar safety feature hiding in plain sight.
So the bottom line here is that understanding and controlling thixotropy is absolutely fundamental to material science. From the food we eat, to the paint on our walls, to the huge technologies that power our world, this quirky fluid behavior is being harnessed to make products that they just work better.
And that kind of leaves us with a final thought. Now that you know the secret of ketchup, think about it. Where else could this amazing property be used? What problem in your life could be solved by a material that's a solid one moment and a liquid the next? The possibilities, really, are everywhere.